My name is Jean-Pierre Papouloute. I'm the Tuskegee University Student Leadership Chair. And as Amy mentioned, I'm an undergraduate student, so I have my pen and pad ready for any difficult questions you guys have for me. But I'm going to go over the germanium and silicon device technology for photonics integration that we're developing here in the lab at Tuskegee University. So here on the front page is the end result of what we want to develop. As you can see, the optical fiber is going in. It's guided by a waveguide, and which is basically going into a transistor. And what I'm going to be talking about is splitting it up into two main parts. The first part being the waveguide, and the second being the photodetector device. So let's get right into that. So first I'm going to give you some personal background and just let you know a little bit more about me, and then I'll go into the general CIAN goals of Tuskegee University, give some background for the waveguide and for the photodetector device, then go over some ongoing developments in the waveguide, what we've done and what we hope to do. For the photodetector, first I'll start with some previous photodetector investigations that were done before I joined the lab, just to give it a little more context. Then I'll go over the ongoing developments of the photodetector that I've participated in. I'll wrap that up with a summary of everything that we've done and everything that we hope to do in the future. And then I'll open it up for questions. So, personal background. I'd like to start off just by pointing out I do have an unusual name, and often I run into problems in this area. So, it's pronounced Jean-Pierre Papouloute. It is a Haitian name, not a French name, not quite. And I am a junior electrical engineering major. So I know a lot of you have a lot more knowledge in this area, and I'd like to learn a lot from you today after I share what we've done and what I've participated in. My hometown is actually Pasadena, California. I'm not from the southern area. And by the way, shout out to Caltech if anyone here is from Caltech. But my hobbies are longboarding and debating, and along with the CIAN Student Leadership Chair representative position, I'm also the IEEE hardware team leader here at Tuskegee University. So there's a little bit more about me, and now let's get into the content of the presentation. So what are the CIAN goals at Tuskegee that we're trying to accomplish? On the right side, you can see more of a breakdown of the development of the integrated device that we want to develop. But in general, the CIAN goal at Tuskegee is to develop that, a monolithically integrated, high sensitivity, germanium and silicon heterojunction field effect transistor photodetector for, ultimately, a silicon optoelectronic chip. So even though we're more on the device side, the silicon side of this, ultimately it is for optoelectronic chip making, and it is about photonics overall. However, in order to achieve this goal, we have sort of mini goals. And in general, we'd like to investigate the high mobility p-channel germanium on silicon MOSFET to reduce the area of silicon in the CMOS devices. Of course, this is a necessary part more toward the transistor than the waveguide. Also, we'd like to develop the processes to form germanium films. Specifically, we'd like to explore how much work we can do with sputtering as an alternative to molecular beam epitaxy. Because sputtering, if we believe there's a lot of potential in sputtering, and if we can show that we can fabricate devices using this process, then we can significantly change the amount of money spent in fabrication. Also, a germanium silicon photodetector development in general, obviously for the main goal of this device, that's an essential part. So, as I said before, our integrated device is mainly made of a photodetector with a waveguide that can carry light from an optical fiber. So some background on each of these. First, a photodetector. Long story short, it converts optical signals into electrical signals, and there's the diagram and a picture of one on the right. We work heavily with photodetectors to test our devices and to compare our devices. And an example of this could be a photodiode or a phototransistor. And we've developed both of these technologies in our lab, and we use them extensively, but that's the general background. Now, waveguides guide electromagnetic waves in the optical spectrum. So for ours, we design our waveguide to respond to 1550 nanometer light, a wavelength of light. And they can have different geometric structures. We've developed planar and strip structures. We don't get into the fiber waveguides as much yet. They can have different mode structures. In our case, single mode is what we've developed so far. Different refractive indexes and different materials. So what have we developed so far in the waveguide technology? What have I participated in at Tuskegee? So far, we've successfully fabricated a sputtered waveguide for the proof of concept. So silicon was sputtered onto a glass substrate, and we sputtered it at room temperature, and we did not post-anneal. So this was one of the cases, the simplest case, where we didn't do any heating to the silicon, which is ultimately our plan, but this will serve more as the control group for our experimenting. Also, we've cladded it with PDMS. Well, ultimately, we wanted to clad with oxide. However, in this controlled test, we actually found that, to our surprise, that the waveguide worked. It significantly changed the difference between, it significantly transmitted 1550 nanometers of light. And we tested this with a photodiode, and there on the right, you can see the characteristic on the graph above. Below, you can see the silicon waveguide and the polymer cladding. And that's what we've done so far this year, a couple of weeks ago. So in the future, for the waveguide, what we really hope to get to is fabricating the waveguide by sputtering at 500 degrees and by post-annealing. So why do we want to add in these temperatures at these different times? Ultimately, we want to get a more polycrystalline structure to the silicon for our waveguide, because we believe in theory that it should be a more effective waveguide if it has heating in the process somewhere along, so it can change into a polycrystalline structure. And we can test this individually. So first, we can sputter at 500 degrees with no annealing, sputter at room temperature, and then anneal afterwards, and then combine the two. And we hope to do that within the near future to see what kind of differences do we see experimentally. Is one more effective than another? We're not quite sure yet. So also, we want to clad the waveguide with oxide ultimately. But we're still open to the PDMS cladding as a final plan if it does test better than the oxide waveguide that we originally planned. We were really surprised to see that the control group waveguide worked at all, so we're going to continue experimenting with our normal plan and then compare the two. So, on to the photodetector. So what work was done on the photodetector so far before I had any involvement? We've already completed several proof of concept photodetectors using silicon and germanium. As you can see, these are three different examples of the photodetectors that we've used, both diode and transistor. And there is a significant difference in different areas of the characteristic, but overall, in the IV characteristic of the photodiodes and the phototransistors that we've made using silicon and germanium, we've seen a proof that this does work. We've developed different device configurations, and we're still developing different device configurations. But this was the work that was done before, and let's get to the ongoing work. Oh, one more thing to mention. The aluminum in two of the device configurations that you see here was just used because it's a cheaper material. but ultimately we know for our final photodetector we're going to use the gold for the source and drain. So we've successfully fabricated sputtered lateral germanium silicon photodiode, as shown in the last one. But that was redone at the beginning of this year. The photodetector fabrication challenges that we're still facing, however, are the center germanium gate and a blister type of damage to the germanium layers. And we think this could be caused by the spin-on doping step that we use here. So we're constantly improving on our fabrication technique. But that's one of the major challenges that we're still facing. Also, we have new equipment in the lab. So we're developing new procedures even for testing. And that's something that's been going on for quite a while. And it's another one of the challenges that we have. Even after we finish fabricating a device, if we mistest it, then we don't want to send the wrong results out to all of you. So we're developing new procedures for testing. Finally, we found that so far we're able to test the voltage characteristic a lot easier than the current characteristic. And we know this is ultimately the more important characteristic. So that's another big challenge for us. So in summary, our accomplishments overall are a proof of concept for silicon sputtered waveguide and a proof of concept for sputtered silicon and germanium photodetector, which is in the diode form. And the challenges moving forward for the waveguide are testing of polycrystalline silicon waveguides, sputtered with temperature and using different annealing processes, and the fabrication and testing of waveguides with oxide cladding. For the photodetector, we'd like to fabricate germanium gate with a smooth surface, center the germanium gate with more accuracy, minimize the germanium gate width, and of course define or redefine our testing and characterization procedures. Okay, so that's it. Are there any questions for me? I guess type them in the chat box. I know that was pretty short and straightforward, but all questions welcome.
I see that Soha is typing a question, so maybe we'll give him just a minute to finish up and see what he has to say.
Okay.
So the question is, why aren't you using silicon-on-insulator wafers for creating silicon waveguide?
Okay. The answer to that question is, at this point, it's mainly for cost. So the silicon-on-insulator chips are significantly more expensive. And since at this stage we're mainly doing proof of concept work, I've been told that we don't want to buy those silicon-on-insulators in bulk yet. Wait. Are these questions in the chat? Okay, here we go. I didn't scroll down. My mistake. Okay, any more?
looks like Soha may be typing one more question, so we'll give him just a second. Oh, there it is. So he says, so would sputtered WG have similar performance and structure with the SOI?
Okay. Yes. Sputtered, that's exactly what we're testing at this point, is we really want to maximize the amount of sputtering that we use in this process just to explore that area of fabrication in general. But we don't know. We don't know if sputtered waveguides have similar performance, so we're starting off with the sputtered waveguides at this stage, and then when we test both of them, we'll be able to give a more straightforward answer.